All right. Good afternoon, everyone. I hope you can hear me in the back. If we need a mic or not, then give me a buzz. Yes? Okay. All right. So I'm Srulevich. Happy to be here with my friend Andrew Kaushal. And I know it's a tough time after lunch, so we'll try to keep it energetic. We're going to talk about signals and data sources. So very, very, very energetic stories, but I'll try to make it a little bit more hype for you guys with some artificial intelligence, some examples to make it lively. Just, interrupt, ask questions, see what's going on, and we'll try to get through this one. I'll try not to keep you the entire hour and a half, so we'll have time for questions and maybe see a demonstration of what we do. But I'll start with what we do. We've been working in the mining industry for probably over a decade, specifically on artificial intelligence, visiting hundreds of sites across different areas from South America to the US, to South Africa, Australia, Kazakhstan, Europe, etc. Learning a lot around this one and meeting with different types of individuals from executive to mining maintenance and reliability and operations and on different types of commodities to learn what's happening above ground and open pit, but also underground, and understanding more how can AI apply into this industry in the most appropriate way for probably the last decade. And the same question that came to mind, I think, over time is why with so many different monitoring systems, and I'm sure you've seen many, you have some, or you've been around for a while, still maintenance become a huge burden and huge cost. And we'll try to answer some of this one and understand the data that we're going to take. We're going to walk you through a process of understanding, specifically on the mobile side, the mobile fleet, from a signal perspective on data sources, what they are, what the problems are, all the way to diagnosis, understanding how do we diagnose it, what kind of rules can apply into this one, understanding the logic of the validation and what the description looks like, but also closing the loop with the specific work orders and how do you verify it's working, take you into a process of how do we see evaluating kind of the value from this one across different mindset and how do they use and try to apply value confirmation into your operation itself. If time permits, we'll talk about delivery, how does it work, what happens if you don't have the data itself, what do you need to do to actually move forward, either with us or with someone that makes sense, but the idea is to give you more information so you can take it and figure out if it makes sense for yourself. So a little bit about ourselves. In a nutshell, we are a publicly traded company working globally with multiple different names, have a very strong collaboration with some of the greater players in the market. Started probably about 9 years ago, building artificial intelligence models in deep learning before it was commonly used. I don't know if everyone remember that a while ago there was no ChatGPT, and there was no Gemini, and there was no Claude Code. You actually did rule-based, and you try to learn what AI does, and you try to confuse what it means, etc. And we were, knee-deep into this one, building models and understanding how it works and operating. I'll share this one with you. We've won numerous awards around the globe, and we can, search us tomorrow or later on to understand how do we actually apply. But we build a very unique capability that I hope I can share with the crew here. But in essence, what we do is we develop an AI sensor fusion for predictive maintenance on both fixed and mobile fleets. And this is what we're going to talk about today. So our operation is globally, North America, from Arizona to Colombia ports with Cerrejón, all the way to Europe and South Africa, and different operations, including DRC, and of course in Australia, where we operate in various different commodities from the Pilbara to gold operation, down south with iron ore, and of course in Queensland and New South Wales and Hunter Valley with coal operation, zinc, etc. Both open pit, underground, but also in fixed assets, and also starting in the oil and gas in Victoria and starting to build the same technology over different industries to try and push this one forward. Everyone has different challenges, but I will try to kind of find a common theme that will probably address the same issues that you guys are familiar with from the mobile side. So when we look at the main problem that we identified today in the market, the main challenges that we have are probably high maintenance cost and unplanned downtime that we see across sites. There is an operator behavior that is impacting actual equipment reliability. And we'll talk about how does this apply and what happened. In some places it's abuse, in some places it's just mistraining. That operator are using the wrong gear or not approaching the right pit in the right time, and we need to actually train them more. But if you don't have visibility into what's going on, how does it work? Now, it works very well in safety sides, right? You can look at the eyelid, you can understand what they're doing. But if we talk about mechanically and understanding deterioration of components, what does the behavior actually say about what we do? I have a a teenage daughter that just got her driver license. I understand abuse of car, of not a very appropriate driver. So there is a lot of this also in the mining side. And of course, there is lack of visibility into what's going on in the fleet and the data itself. So I'm going to walk you into kind of a 4 steps of methodology that we use to examine what's happening from a data sources into the diagnosis phase, into understanding what it actually means and what they need to do with it, into how do we work a closing work order? What happens if you open it? How do you close it? How do you track it down? And how do you figure it out? So let's jump right into this one. So in the sample side that we look at, there can be multiple different data signals across the fleet. In one of the sideways, imagine you have 100 different trucks, 100 data points for each, 10,000 data streams that are generated every second, creating about 700 different alerts per week. In this site, for example, there's only 3 condition monitoring engineers that are actually working on this one, trying to understand the noise between all of this across all alarm, all fleet, all different types. Unfortunately, it's not always the same fleet, the same model, the same way it was created. It's accumulated over time with too many different variations. It's almost impossible to ask human beings to understand from the noise what is going on, which create basically a failure that is consistent. Many failures are missed. Many things cannot be done. The team is trying to understand what is going on through the noise, and they're doing their best to actually understand the specific issues that they can track, but many of them fall between the issues and the threshold and lost in the crowd, which result in ongoing maintenance cost deterioration that are unplanned, untapped, and really cannot be touched. So where do we see existing system falling apart or missing? And you may have more systems than I've highlighted here, but not to promote anyone, but great companies doing really good stuff, but they're not doing everything. And you have a mixed fleet that you need to control and understand what is going on. So there's too many false alarms we're going to touch about this one. You don't understand what's going on and how does it work. If you have hundreds and thousands of different alarms, we'll talk about this one, right? It's impossible to see it. There is limited availability of reliability experts on site to actually understand what is going on. Even if you have a problem, you have one person, 2, and you have a fleet of 100, 200 different vehicles with too many alarms, too many noise coming up. What do they deal first? You just put it on a planned maintenance, and that's it, and hope for the best. Late detections is what happens when you hit the OEM alarm, right? There's a threshold, but we understand that when you hit it, it's already too late. So why in the human body we can understand what's happening before you're severely ill and you can do examination? In the trucks, you cannot do it. It doesn't make sense. We'll talk about this one. And of course, there's no visibility into operator impact. What does it do to the vehicle itself? And we try to approach it and figure it out. Now, I want to look at one example, and this is one example of, I'll move it away from the mic. So one example is, you look at a variety of different vehicles that we're looking at, right? And then in a single week that we had, right, in August. And you can see that in a single truck, you can see about 62 different critical alarms that were recorded and about 600 alarms overall that are coming through, just not serious, right? How do you scan through all of those in a regular business day, figure out what's going on within your allotted time, get it into action, open the right work orders, and make sure they're all tracked, implemented, working well, going back tomorrow and verify it's actually done well? When you multiply this one by a fleet, we're talking about hundreds and thousands that are happening every day. It's a real problem. And fleets are having a hard time every day. You can work with the OEM to provide you specific data, but then it's maybe one OEM provided, the other one doesn't provide it, and the depth is not always as you need. So manual investigation are extremely hard. It can be done. When you go into telemetry data, and not only alarm itself, you can see the vast majority of the data is available. We can share it, right? This is our screen. You can actually see all of the data. But asking a human being, asking your teams to go through all of the data, scan, crunch, and figure out what's going on, it's almost impossible. It's not fair exercise in today's world. And we can see that despite their large effort of actually accumulating those, you get the data, you can't really understand what's underneath. So you can find different 60 plus patterns across different sensors that you have on the truck, right? You can see additional operation signals to understand the actual machine context. You can see specific 10 oil patterns, and we're only in the air and exhaust system, right? And there's a variety of different sources and mechanical issues across the fleet itself. And the question still becomes, how do you maintain and control all of those together? I think this is becoming a real issue. The next piece is about how do you find expertise to actually help you understand the data itself, right? It's very hard to find experts for remote sites. Typically, sites are not based in Sydney or in Manhattan, right? So getting them to sites or getting them on the call or getting the right time is very hard. Limited availability of the OEM itself, they are available for you. Sometimes they're available too late. When you ask the data, they will come and say, yeah, here it is, but too late. And the question I'm hearing for different CEOs in different tier one companies, well, if you know it, just tell me, right? I need to know about it in advance, not after the fact. And if it's after the fact, how good is it for me for the next time? I need predictability. I need to know what is going on. So there is a lot of data held within the OEMs. Not everything is shared. And if it is shared, it has a cost. And if you already get it, what happened with the other fleet? I think mixed fleet, we talked about this one as well. So we talked about the data itself. How do you decipher it? How do you understand what is going on with the data itself? Now let's talk about what happened with the actual health pattern. How do you analyze it? We have a lot of alert, a lot of noise. We want to understand the root cause intelligence that comes together. So at the end of the day, we want to be in a position that we can control and analyze multiple sources of data all at the same time and understand if there are hidden patterns behind it in order to give you the proper indication of what to do. The team on site doesn't care about AI or modeling. They want to understand what's the root cause and what do I need to do and verify after the fact it's actually working. So I think we build a platform that basically embed this kind of mechanical knowledge into the platform itself. And I think it scans thousands of known multi-signal approaches and really recommend for you what is the right approach to actually take it forward. And I'll touch some example of those. But think about it like an out-of-the-box expert level in your pocket in a way that we kind of use ChatGPT today, right? Or Gemini or Claude, etc. That someone that understands, but we'll talk a little bit later about why LLMs are not really good for what we're trying to achieve right now because it's not trained on the right data. So we're trying to tell it where, but we're very interested in telemetry data and it really cannot read it extremely well. So let's look at one example. I don't think it works, but I think you can see it here. So here's an example. I think some of you will understand it, right? So we rely on a threshold. And I took very, very simplistic example that you may understand extremely well. Just an alert-based simplistic approach to lead to really missed failure. On the left-hand side, you can see that, operating in a healthy environment, right? You can see the fan and the coolant, and you can see that the fan is cooling, it's working with the coolant really to see the threshold itself. You can see that when the fan below is working high and the temperature is rising, it's cooling it off and it's working as expected. On the right-hand side, you can see that the coolant temperature is rising still below the threshold of the OEM. But you can see a failure hindering inside where the actual fan, instead of being up, it's actually going down. Now, this is not something that will be noticed. There's no alarm coming up. There is a small failure coming in. We can see increase in temperature. We can see a failure. Instead of cooling, it's dropping the speed itself, doing what it shouldn't be doing, creating a failure that is emerging. That's what we're talking about, understanding underneath. Now, you will not get a failure. Nothing will alert and jump for you because there is a threshold. It will never come up. But think about this example and multiply it by 1,000. What is happening underneath that is deteriorating your machines without knowing about it? You don't know. Now, we want to see the signals before they emerge. We'll use the tsunami example, right? The birds are flying and the water retrieving way before it hits the shore. You want to know it beforehand. So you can actually say, I see a signal here, as microscopic as it can be, or as advantageous as it can be, in order to say, you know what, let's plan this one, replace some of the trucks. I'll handle those beforehand. Knowing it after the fact, create ongoing deterioration. This will be the theme of our conversation. Predictive maintenance is about knowing in advance what is happening so you can make better decisions. It's not here to replace any work of everyone by putting a robot that will control the world. It's giving you better decision making and actual accurate actions to push the ball and actually get through the entire process. Another example will be the entire fleet itself. So you can see here, we're looking at a comparison of the entire fleet. So you can see all the fleet's elements in the graph itself. And average is what we see in the middle of the screen. This is the average of the entire fleet, right, in the coolant. But you can see a single truck that is spiking higher, right? Still under the threshold, but still spiking higher. Wouldn't you want to know why? Higher temperature, yielding tons of difficult issues, creating deterioration. Nothing works well when it's too hot. Why would you want it to happen? When it's deviating significantly, the lower part is within a threshold, this one is spiking up. You want to know about this one. In the current threshold environment, it will not be noticed. It will just go as is, and it will, at one point, spike. Then get an alert, and maybe you can understand what's going on from the thousands of alerts you have in the system itself. So understanding those signals and doing this kind of a comparison across the fleet is not an option, it's mandatory. Across all of your fleets, across all of the engines, across the component, and this can be done automatically using artificial intelligence or different capabilities that you have to look at everything together, understand the anomalies, and understand what needs attention. Another example I want to show is when we talk about kind of temporary operation condition that can be triggered by an anomaly, something that doesn't really make sense. You can see the vehicle speed on the bottom actually rolling, and then when it stopped, for some reason, there is a spike. Maybe the driver was, pressing the throttle for some reason, doing something that he shouldn't be doing. Create a spike, create alerts, 10 alerts. On this single event, just creating an alert. And there's no problem here. There's nothing really wrong with the system, but going into false alarm is what drags the maintenance team into an overload, exhaustion, and really don't know how to decide what to do. Now you get those alarms, in addition to many other alarms. How do you understand if this is a real problem or not? And this is just one simple example of what can happen on a single truck, on a misoperation. And maybe this one is pure training or just non-issue. So not doing rule-based or threshold-based monitoring puts the smarts into the game itself and giving more indication about what actually is happening. So in this case, there's absolutely no issue, right? It's okay. There shouldn't be any kind of spikes in alarm or alerts. Now, I want to touch a little bit about how do all of those examples actually fit into our new world of artificial intelligence and what's happening in today's world, and why can you just plug all of this into ChatGPT and tell it, here is my data, just give me the answers, right? It can write my emails, it can find me a flight, it can hallucinate sometimes, but no matter what, or why can't we actually work with this? And I see the answers comes to how does those large language models been trained? When those were invented, they were trained mostly on textual content, right? Mostly, Reddit and YouTube and others, less on our mechanical and deterioration processes that we intend and we work with on a daily basis. They're not meant to actually understand and extract telemetry data in large scale and equivalent behavior in order to provide you patterns. Can you do it? Maybe on a small scale. Can you develop a platform to analyze it? Probably, but it requires training based on known facts, right? When you train a model in the most simplistic manner, right? You want to train it on things that you know. You take 1 million pictures of a cat and 1 million pictures of a dog, and you tell the model, this is a cat, this is a dog, figure it out. I'm not sure there's enough examples out there right now to provide an engine with all the failures that you're familiar with, I think it's 6 times, to allow train the models. So it's very hard. How do you train it when there is no enough examples, nothing is really tracked, and there's no clear coherence between what you have, the logic, and the individuals? And this is where we come to play, and this is how we take an action on this one. So it's impossible to support this one. It doesn't understand the equipment itself, and I think the data that they have is very generic, so the result that you will get will be extremely generic. So it's not really suitable for predictive maintenance on mining equipment, as we've seen. Now, what have we done? We have decided to actually create numerous expert models. So we have trained our system using experts and knowledge. So we call it semi-supervised learning, where we actually apply our learning, think about the LLM models before they were widely adopted, using experts. You put individuals that are experts in the market, Komatsu and Caterpillar and Hitachi, use it on fixed and mobile assets, and you get the knowledge that you will ask your own team into a model of a learning. So as we build the models, we have human expert validation over the past years in order to verify that what we do actually makes sense. So this combination is what was missing because there's otherwise no ability to do it. And we started early on, so we have an advantage of having this kind of a library available for all trucks and all equipment. And this is kind of where we're going. So we have broken the component into 3 different phases. We call it early detection, root cause diagnosis, and operator behavior. And you can find many others that are maybe missing, etc. And we keep on growing this one, but it can be from a torque converter, it can go into root diagnosis of specific models, all the way to tires and bursts in sharp turns, etc. All of those models that are built with thousands of different examples that you can easily apply without any training mode that is required on your specific data, because it goes into what we call our generic data mine AI system. When we take all those sources of data into the 3 different layers that we have, think about it from a different perspective. We're creating a multi-layer approach of this sensor fusion that keeps on learning by itself. So you add more trucks, you add more capabilities, keeps on learning, giving you the opportunity to get more benefit from the models themselves. And as we add more data, and we do happen to find different trucks that we haven't touched, or different manufacturers, it's not very common, or sometimes you find vehicles that are way too old, right? They don't even have sensors on them to actually accumulate or extract the data for us to train it. So we're either going to install a data logger that Andrew will talk about shortly, or we actually use our pre-built mechanism to tell them what is going on. We push it forward. But this kind of a feedback loop is helping us to know what is going on, and the inspection of the data to make sure we close the loop and figure it out. All right, so we talk about data fusion across different sources that we have. It can be onboard sensors on mobile fleet that we have. It can be fluid analysis. It can be maintenance data, tire dispatch data, everything that you have in your organization. Not everything is mandatory, but it's a good starting point. We feed this one into the models that we have, which feeds into a platform that allows you to see the actual data and recommendation that we'll talk, of course, next about what it is. So before we start moving forward, I want to talk about 2 separate components, right? One is the early detection itself and understanding what operation mode actually means. So when we talk about early detection, you can see the noisy signal that is extracted from the truck. Different sensors provide different type of data. All of this is available, but it's going to be hard to look and compare them in a single time. What's the failure? What's the spikes? What does it really mean? And we need to do a better job understanding it. What we actually found is that a different truck behaves differently when it's in full load or half load, when it's full speed or half speed, different behaviors of different drivers. How do you crunch it into an operation mode when it's uphill or downhill, depending on the load itself? We actually apply operation mode algorithms to allow us actually crunch the entire graph into a more visible identification. So the same graph now transformed into a much simpler to review graph. You can actually compare it. You can see what is going on. It's easier, it's cleaner. It will show you the right trend based on the operation mode itself. So when it's in full load going uphill, it's one thing. When it's half load downhill and it's stopping it, it's exactly different mechanism. So doing those and jumping between your full signal that you can see what is going on into your operation mode signal, eliminate the noise and looking at the very specific problems as it happened along the way. So every time it's full load uphill, it's an operation mode, we will track the same condition over and over again. And there can be multiple different operation mode. This is what we compare. We don't compare noise to noise. We don't compare thresholds. We look at the specific operation over time. And this is what you can do to compare it over different vehicles, right? So that's the idea behind this one. And how do you actually work with noisy signals, shorten it, make it clearer, simpler, and give evidence to the crowd itself. To make it a little bit simpler, when we talk about one of the transmission loop temperature example in one of the Caterpillar trucks, you can see the upper signal is very noisy over time, and we can look at the alarm when it will hit the signal on the top. You can see that the OEM alarm can happen a month later. We can actually identify this a month earlier. So when we look at the signal and we understand the trends coming up, the colors actually indicate our methodology of when it's turning from yellow to orange, and actually indicating moving from just early signal to alert, pay attention. When it's red, you need to do something, but we want to give it to you way in advance. But knowing about it a month in advance, because we can identify the signal, almost impossible from the top tier. I'm not saying impossible, right? Sites have really good teams, but it's only 1 or 2 guys or girls. What can you do? How much can you do with the work itself? In 2026, with the capability in the market right now, you should be able to have almost like free agents working for you, or smart technologies that do the work and give you indication to filter the noise and crack it down. Another example about a fuel injector failure that we'll see it along the way talks about what happened when we compare the load based on the speed itself, the throttle itself, but also on the exhaust, on the right and left exhaust, and the variance between them. So the middle graph is showing the difference between the right and left exhaust temperatures. So when it's spiking, it means something is wrong. It shouldn't be. It should be probably around the same level. When it's spiking, something is indicating a right or left different indication. And what we've seen is that in full load, and the throttle was pushing very hard, you can see a very significant spike between them, meaning there is an indication of a problem. Now, this was done because we're crunching multiple different sources all at the same time in this specific mode. Now, we were able to rule that this is not a turbocharger or an air leak that were not relevant to this one, although they may be indicative to search it in the shop. So when you take it to the shop and not in the field, and you don't know the specific operation mode, the experience will fail, because they will look at it, they will try to replicate it, they will see an alarm coming up, and they will go and they will replace the turbocharger and the air leaks. And what happened? We'll go back again, increasing the same problem that actually missed the root cause because there is no easy way to understand it. So we're trying to give indication by crunching different sources in a way to give you better decision making, so you'll know what the problem is. Keep on changing the turbocharger doesn't really solve the problem. And like this, there's many different examples across the fleet that you're either over-maintaining or you're doing the wrong maintenance, or you don't have even maintenance verification to know that what you've done is working until the next maintenance cycle. And what? Threshold mapping is the right one? Not always. And we're offering an alternative to make better and smarter decisions, to actually push the boundaries of what you can do. I want to move into actionable insights. So we talked about the diagnosis part, and we talked about the signal. Now what? How do you actually get from a failure mode to the root cause to the recommendation itself, right? You need answers. The teams on site don't have time to start playing with graphs every day. Management don't care about everything that's going on. You need to start pushing forward and to get more or less maintenance and push things forward. And the idea behind it is, how do we deliver the failure mode and root cause analysis in a very simplistic manner, English, that folks will understand on site no matter who they are. It's not a data scientist exercise, right? So you need to find and do kind of this hand-holding process and actually do some weekly reviews with them to understand. It's a self-sustained system, but I think bringing experts from the market, where we as an example have it, but I'm sure others as well, bring it on a weekly call with the team, seeing what's going on and says, you know what, that's interesting. We've seen something very different. What have you done? Scratch their head and talk to the site team that doesn't really have someone to talk to on a regular basis because they're buried into the work every day. So I think decision maker will get more clarity, not creating more work and more complexities. And no, this is not creating 100 more alerts or more examples. The idea is to give you actionable insight, and we're going to look into some of those as to what we're seeing. So you can see on the board itself, and we'll try to deep dive into this one later. The idea is you can actually see the specific examples and the observation that was created that gives an explanation to the site about what needs to be done, what's the action. And the action are very crisp. It's not a highly potential or what's going on. It's a very simplistic English. And the idea behind it is to create, I think, a level of trust between the teams and the engine that is calculating this one and telling them, because no one likes to do extra work for nothing. And we've been working in the industry for decades now. It takes time to build trust, right? And here in this example, you can save a couple of days of production lost on this unique example as the fuel injector that we looked at before, because you can identify it a month earlier. But how do you build trust with this one, with the team, to actually go search and actually do the recommendation that is, I think, presented here, and identifying before performance issues happen or break down? And the way we do it is by actually building, trust between the artificial intelligence platform and the user. So our recommendations are tied into evidence. The team on site understand their data. understand what's going on. They just don't have enough hours in the day or weeks in the month to actually do the job. And everyone is cutting sources and there's not enough people, not enough smart people. Providing an answer is not good enough because no one believes it. Providing graphs and technology to do more validation doesn't help anyone. So merging those together is probably the key. So we provide the evidence into what is going on and connect it into the specific graph. What did you see? When did you see it? Why does it make sense? Over time, you start building confidence. I don't know if you remember 3 years ago, ChatGPT started, it was hallucinating, giving you stories. What was 10 plus 10, 20? No, my wife says it's 15. Okay, your wife is right. 10 plus 10 is 15. This is how it used to work, right? You have to build trust. We know what we're doing, but you need to make sure the crews on the ground are operating. So you can see this one and validate every time what is going on. Over time, they will shift from looking at graph, verifying that we can crunch the data into, all right, I can see the results. Let me push a work order. Let's get it out to the teams and let's verify that it's actually working. Which leads me into kind of the last piece of those, 4 quarters. How do you verify that once you identify something, the teams actually take an action? Tons of other things happening. How do you verify it was done? How do you verify it was done properly before you move on to the next one? Sending a truck, now having it again in 2 weeks, still having the same problem, happens a lot, right? How do you verify this is going on? So the idea is to get the information that we acquire into any CMMS, SAP or others to push it forward, right? Get a work order or PM notification, right? Directly into the dashboard itself and actually have a life cycle that controls from A to Z, from diagnosis all the way to close work orders and even beyond to verify the cycle. And what we've seen that some of the systems out there today, if not all of them, are dealing mostly with the work orders. You have a work order, it closes. It doesn't verify the tail. It doesn't verify before and after. And we went to teams and they're working with Excel and they're trying to track this one, what's going on. And when it's ready, they push it into a work order. Then they take it forward. And then when it's done, it's closed. Then what? How do you track it back into what happened? And what happened if it's happened again? How do you know that you've done it? What is the maintenance verification process? So I think those 2 parts of kind of outside the scope itself is something that we've added in order to provide this kind of a clarity, allowing you to push, to start working on work orders before they need to be submitted, manage and track them, understand what is going on, have the capability in your fingerprint to see everything. When you decide, push it out into your SAP or any other system that you of use. And when it's done, take it back, right? Control it and look at what's going on. Identify the actual, it's green, so I don't know if you can see it, like verify and resolve. It's here, you get thumbs up. The system keeps on learning what's going on. You identify an issue, it's coming back, you track it down, it's verified, it's locked. Now you're ready for value confirmation. How do you know if what you've done actually made an impact on the business? Yeah, fantastic. You created 10, 20, 50 different really massive saves on an engine, on a turbocharger, you push the life extension. How do you quantify those? And then we all measured on the success that we bring, not just the technology or the efficiency or, I don't know, a really good looking API or platform that we provide. You need to push this one into value confirmation. The way to push it into value confirmation is to look at, I think, 4 different pillars. One is to pick the relevant KPI for you, right? It can be an unplanned downtime that you have. It can be maintenance costs. It can be other elements that are impacting the site itself, whether plant constraint or mine constraint, open pit, underground, connectivity issues, blockages, you name it. Map the fleet and the history that you have, right? Extremely new fleets behaving differently than the one that was created, was assembled 30 years ago, right? Underground fleet that has no connectivity might be harder to monitor and understand what's going on. What kind of issues can you detect? Early, prevent, or extend the life of components so you can modify those and actually confirm where is the return of investment. Where is the main bottleneck, right? In the open pit and the fixed plant, you can see if a conveyor fails and it's the beginning of the process, you're stuck. Underground, it's stuck as well. If the drill rigs are locked, then what can you do? If an excavator is locked or different parts of the fleet are stuck, what can you do to actually maintain and figure out where is the, let's call it the bad actors that we need to get out of the way get them handled, figure out what's going on, and don't repeat the same failures all over again because it's a routine process. So one example is on how we helped organization actually understand the breakdowns. And we just took kind of different types of scales, looking at the amount of failures and alerts that were happening and the different type of component that we have here. And you can see that we have selected a few of them here just to create representation of different systems that are more interesting. So in this case, we can select the engine and the tires and others that are very significant in a single site. And you can track those and figure out what's inside. You can deep dive into the engine itself, into the subcomponent, and understand what underneath actually is more important for the site itself. So you can start tracking those and make sense out of those. Those will be quantified into a calculation. So the calculation itself actually helps you understand how sites are looking at quantifying a failure. What does it mean? After we identified, we fix it, we work with it, what do you actually do? So you can actually take this one. We take the maintenance cost, which is basically the component cost, time the damage rating that you can put on this one. Is this 10% or 90%? The rating itself, the impact that it will do to the business, and actually the remaining life factor that comes together. And you combine all of those into a cohesive answer. Is this failure something that is worthwhile for us and actually makes sense to actually invest time in a technology or even an improvement, or it might not be as important, so you push it forward and do the calculation. This comes into a whole table, right, where you track different kind of failures from a return on investment perspective. You look at a single failure, right, and it can be any one of those, right? It can be a transmission leak, and you can see the observation and the action that comes together that's recommended by the system, and you can see that the site itself will decide what data does it put on the downtime, on the spare parts, on different cost elements inside to actually accumulate this one and verify that the case works. I want to talk about the last piece of this portion, which is component life extension, that I'm sure everyone has experience. So when you talk about component life, in this example, you look at what the manufacturer recommended, maybe 20,000 in this case, right? You can wait for this one, see what's happening, replace it. Either you maintain it or a vendor, which is fantastic. The second part will be what happens if you're using condition-based maintenance, where you either maintain it before, or you apply it before or after, but it's not really tracked. It's based on what actually is happening with the condition of this specific component itself. But we recommend an alternative. And this alternative is to actually look at what if along the way, when you're identifying a problem, you can actually fix it soon before it will create damage to the component itself. And those accumulate over time. So when you identify a problem with a coolant or an engine or an oil pump, etc., and you fix it before damage was created, now the overall impact on the component itself is much lower. It's before signal is happening. Overall will create an impact for you for even 1,000 more hours, maybe up to 25% increase if you're able to increase all of those, identify those in advance, and figure out how does this happen beforehand. And this is, I think, what we're trying to achieve is pushing away, expensive replacements if they are not needed, pushing away lack of understanding of what the problem is, knowing what to do and have a better decision-making to push the boundaries of what actually can be done with identifying and knowing how does the predictive maintenance system works like this. It all accumulates into a table like this that we've seen before that has the list of parameters, understanding what's going on, the impact that this has, and what kind of a component extension and life it will do, not always in a dollar value, although it has, but also in a production, replacement parts, etc. In large fleet that we deal with, some of our customers has 1,500 vehicles out there, right, on the big trucks. It's a massive impact on the organization to even reduce 2% of the maintenance cost. Even extending the life of certain component, push CapEx away, allows you to, over the life of the mine, really push the boundary of what you can do by actually using the data. To summarize, we've started from signals, we pushed it over into diagnosis, then we understand what to do with the diagnosis so you can have results and you can see what it actually means. Capturing this one into a work order, feeding it into a system and verifying that it's working, and then looking at what does the value look for you across all of those, from failure prediction or from extension of the life, etc. I'll hand it over to my friend right now to talk a little bit about how do we deploy those, some experiences that we have on the ground, if you have data or if you don't have data. Any question beforehand?
Thanks, Omar. The same way as our system, the deployment is also very simple. It's a 3-step process. And the very first, we'll do the vehicle survey. Second step, we come over and do the deploy and install. And third step is going over and apply the installation. So when we're looking over on the first step, we're talking about where we need to capture the data. We have like a data logger like this. It's a size of like iPhone. We go over and then install it. We work with all different types of OEMs. We can work with all the different types of trucks. Doesn't matter whether it's a Sandwich, or Cat, Komatsu. We come over and this comes with the both for Wi-Fi as well as the same 4G connectivity as well. And it contains all the ownership. Now, there will also comes over many of the times I have heard the questions, what if there is a no network connectivity? What will happen then? So this stores up to 7 days data. And so that you have, even whenever you don't have a connectivity, it stores the information. Once it's back to the connectivity, it's stored, share that information, upload it on the platform. We work in the scope. As you can see, this is just to share some of the examples. We work all different types of Komatsu, Caterpillar, Hitachi in the open pit space. We work on all different kind of fleets. Same way in underground as well. We have a scope of all undergrounds as well, Cat, Sandwich, all different assets that we work with. Now, when we're coming over on the very first day and our team is coming over to doing the vehicle survey, what exactly in that day of survey we are covering? So we're looking over this is an example of Cat 789. We look over where exactly the Cat cabin is, where the data logger will be installed, and then we're looking over the antenna locations. All these things our team will look over, and it will be looking over the size of the measurements from antenna going back to their cabin. Same thing for underground as well. So we look over and we try to place it in the very safe environment. It's inside the cabin, and just to make sure that it doesn't get damaged. So in the very first step, as we come over in the vehicle survey, we look over the model, we look over the interfaces, what is the installation points, all these things we cover. So that once we're doing the installation, actual installation, there is not any surprises coming out. And we wanted to make sure that there is a minimal downtime and the whole thing is configured very quickly. Now, each data logger, we were talking about approximately 2 to 3 hours of installation. So by the time your truck comes to the workshop, we install it and it's the same thing. Then in the phase 2, when we start looking over, our team of expertise will come over, they will work with the site team, with their Sparkies, we'll work very, very closely. We'll install it, we'll secure the mounting, the harness routing, and then we'll configure the platform. So in the second step, we'll pretty much doing that. It's a very fast installation. And as I mentioned, that will be like take 2 to 3 hours and get done and it's ready to go. And then in the third step, pretty much in the phase 3, it's go live. So when we leave the site, as Tomer highlighted, that the models are already trained. So we're not training the models again. So it's the moment we leave the sites, it's already live on the dashboard. That's how it works. It's as simple as that. Now there was a question, and another where it comes over like, what if we don't want to install the data logger? What about if we just use our telemetry data? And not everyone is like, okay, use our existing data and tell us what you can see. And there was one of the examples with a leading miner who gave us the telemetry data, and they wanted to see what the results are. And we analyzed the data. It took us a couple of days. We went back to them the same week, and we showed it to them. We said, last year you had an alarm, critical alarm, in October this time. They went over and they said, okay, let's validate with our maintenance team. They went back and when they came back and they said that was a critical alarm. What happened really over here? And they said, oh, because we get so many alarms, we missed that alarm. And what it lead to the failure of that equipment. So this is closing the loop. What Tomer highlighted earlier, that when we have like data, you have the visibility, which is you can see it on the dashboard itself. So it's that simple as that, the process in the deploying the data loggers or using the telemetry data. And then we have a pretty much AI system. Any questions?